Hi everyone. In this video, we're to cover section 2.3 titled The Limit Laws. Okay, so we start out with these basic limit results that we were introduced to in the previous section. 2.2 is all about introducing you to limits by evaluating functions really close to the number that you're approaching. Now we're going to get some more precise procedures for how to evaluate different limits. So we're reminded of these first two limit results. The limit of as x approaches some number of the function y equals x, or f of x equals x, is that number. Go back to the last video if you want a brief review of why that is true. And the limit of a constant function, regardless of what I'm approaching, the limit of a constant function is that constant. It doesn't matter if I'm approaching 1, 2, 3, 4, 5, 6, 7. If the function is a constant function, the answer is that constant. Okay, so two quick examples using those two basic limit results. So part A, it's the limit as x approaches 2 of the function x, which is 2. B, the limit as x approaches 2 of 5. It's a constant function now, so the answer is that constant. In the explanation I gave in the previous video, that function is a horizontal line. The y-coordinate is always 5. It doesn't matter what x I am approaching. The y-coordinate will be 5 forever on that function. In part A, if I'm approaching 2, on the x-axis, I'm approaching 2 on the y-axis, because that one is the line y equals x. The y and x coordinate are always the same. Now we can use those two basic limit properties to then come up with all of these different limit laws. So go ahead and pause the video right now if you want to read through each of these. I'll kind of just overview, briefly talk about the important aspects of it. All right. The first one, sum law for limits. As x approaches a, if I have a sum of functions, but really that's a sum of different terms within a function, right? I can evaluate each limit individually, all right? That's what that first one says. If I have a collection of terms that are a sum of terms, I can look at each individual term separately and evaluate their limits. Same deal for differences. If I have a limit of a difference of functions or terms, I evaluate each one individually. The constant multiple law, if I have a constant in front of my function term, then I can factor that constant out in front of the limit and just look at the limit of the function. So we can factor constants out in front of our limit to make things easier to look at and process. Our product law, if I have a limit of a product of functions, then I can look at each piece individually. Okay, quotient, if I have a limit of a quotient, I can evaluate the numerator and the denominator separately, provided that the denominator is non-zero. And we'll get to problems where it is 0 and what we do then. All right, same deal for powers. If I have a function raised to some power, I can focus in on just the function, worry about the power later. And then my root law, if I have a limit of a root, an nth root of a function, well, that limit I can worry, again, just about the function term and then deal with the root. Okay, so how do we use those limit laws to evaluate limits? So our goal is to be able to evaluate more limits here. Actually, let me just move this up a little bit so that I can have both on the slide at the same time. Like that. There we go. All right, so our example here, we have the limit as x approaches -3 of 4x plus 2. So I'm going to rewrite that problem first. Limit x approaches -3, parentheses, 4x plus 2. All right, so the first thing that I see is I have a sum. So I'm going to use the first property, the first limit law, and break this up into the limit as x approaches -3 of 4x, and the limit, or plus, excuse me, the limit as x approaches -3 of 2. So we've separated our limit up into two separate one limit up into two separate limits, I guess I'll say. Next one is we're going to use the constant multiple. So we use the sum law first, and then the constant multiple law, because in here I have a 4x, 4 times x. So that constant multiple law says that that constant multiple of 4, I can factor that out in front. So this now becomes, this is equal to 4 times the limit as x approaches negative 3 of x, because I pulled the 4 out, plus the limit as x approaches negative 3 of 2. All right. Now, here's the big, well, not easy step. Here's the big, like, pulling it all together. The limit as x approaches 3 of x. That was addressed on the previous slide. The limit as x approaches negative 3 of 2. That was approached on the previous slide. So, to kind of finish this off, we have a constant function here. Its limit is always the constant. The limit as x approaches negative 3 of 2 is 2. It's a horizontal line. And then the first term, 4 times the limit as x approaches negative 3 of x, right? The x value is approaching negative 3, so the y value will also be approaching negative 3. So we take 4 times negative 3 is negative 12. Add 2. Oops, I lost my negative sign. And you get negative 10. So the value for that limit is negative 10. Now you might be saying to yourself, this seems horribly inefficient. There must be a better way. You know, what if there were like 10 terms? Would I have to write the limit 10 times, you know, for each line of the problem? Again, it seems very inefficient. Well, hang on. This top theorem 2.6, this tells us something super important, that when we have a polynomial function, p of x, q of x, the limit of that polynomial function as x approaches a is p of a. So what that means is that if you have a polynomial, just evaluate it. The limit is what you get when you plug in the a value. If I have a fraction, a rational function, the limit is what you get when you plug in, substitute the a value, provided that q, the denominator, is non-zero. We'll get to ones where it is and what you do. But for now, step 1, after you understand limits and what they are in terms of approaching the number, step 1 to evaluate a limit is just substitute and cross your fingers. If I can just substitute, I'm golden. This problem is a piece of cake because I'm really good at plugging and chugging. All right, so let's see what that looks like in action. Here we have what looks to be a terrifying fraction. The limit, let me write this one down. As x approaches 3 of 2x squared minus 3x plus 1 over 5x plus 4. So to evaluate this, this is just the numerator and the denominator evaluated at 3, provided that we don't get 0 in the denominator. 2 times 3 squared minus 3 times 3 plus 1 over 5 times 3 plus 4. Lost a parentheses. I don't think I'm going to get a 0 in the denominator. This is great. 5 times 3 is 15 plus 4 is 19. 3 squared is 9 times 2 is 18 minus 9 add 1. 10 over 19. Boom. Done. That's it. That's what this function is approaching. So what that means in the context of like a graph, if I have a graph of this rational function, as x gets closer and closer to 3, the function, the y value, gets closer and closer to this weird fraction 10/19. That's what that answer means. Now, to begin talking about more techniques, more strategies by which we can evaluate limits, let's take a look at these two graphs here. The first is a pretty basic line, g of x equals x plus 1, right? It has a slope of 1 and a y-intercept of 1, right? So we go up 1 over 1, up 1 over 1, etc. All right, the next one looks much more complicated. It's a rational function, but all that complication of this fraction does is it drops a hole into the function. This function, or this fraction, excuse me, does not exist when x equals 1 because we have 1 minus 1 in the denominator, and what that does, in effect, is it puts a hole. That open circle there means that the graph does not touch that point. But what I want to talk about is what is the limit for on both of them as x approaches 1 for both functions. What is the limit as x approaches 1 of g of x? And what is the limit as x approaches 1 of f of x? Well, looking at the graph, here's 1, here's 1. As I approach 1 from below, as I approach 1 from above, it looks like we're getting closer and closer to a y-coordinate of 1. And we are, in fact. If I plug 1, if I substitute 1 plus, or it looks like we're getting closer and closer to 2, excuse me. 1 plus 1 is 2. That limit is equal to 2. Now on the rational function, the fraction, what do we see happening visually? Well, as I approach from below, as I approach from above, it seems like we're still getting closer and closer to that y-coordinate of 2. Even though at exactly 1 we're undefined, we're getting closer and closer to the y-coordinate of 2. All right, but what now? So this limit is 2. Both of them are 2. But what's the difference between the two functions? Well, let me zoom in here on my notation for f of x, or my function f of x. If I take that fraction and look at it a little bit differently, x minus 1, the numerator, remember factoring in some math class in the past? X squared minus 1 factors into x minus 1 times x plus 1. Oops, plus 1. There we go. Okay, so that fraction, that numerator factors into those two terms. And then if we think of this x minus 1 is canceling out, well, then the two functions are the same now, right? X plus 1, x plus 1. Right? What that extra term or extra expression, the x minus 1 in the numerator, the x minus 1 in the denominator, what that does to the graph, what it does to the function, that just pops a hole in it, right? And so you can do that with any line you want to. If you have like, I'm kind of going off on a tangent here, but well, just stick with me for a minute. If you have the line like y equals 3x plus 2, right, that has a slope of 3 and a y-intercept of 2. If I want to put a hole in it somewhere, right, I don't want to change the graph at all. I just want to like make a hole in the function. All you got to do is rewrite it as y equals 3x plus 2 times x minus 5 over x minus 5. And you simplify that and you'll trick people. There will be a hole in it, right? That has a hole when x equals 5, but it looks identical to y equals 3x plus 2 other than the whole. Okay, so I again went off on a little bit of a tangent there. The idea here is that the two graphs are the same, the two limits are the same, and one strategy that we can use moving forward is factoring, and then we can look at our limit. So let's do that in this example down here. Right there. Evaluating a limit by factoring and canceling. So we have the limit as x approaches 3 of this fraction, x squared minus 3x. Actually, I'm going to write it out. Limit as x approaches 3 of x squared minus 3x divided by 2x squared minus 5x minus 3. All right, and just to be sure, if I substitute 3 squared is 9 minus 9 in the numerator, and then in the denominator, let's see, 3 squared is 9 times 2 is 18, minus 5 times 3 is 15, minus 3. Yep, I get a 0 in the denominator and a 0 in the numerator. Okay, so I need this new strategy, and the new strategy is to factor. So the first thing, when I rewrite this next step, I'm going to write the limit as x approaches 3. Right? That carries on every step until you write the answer, until you quote-unquote take the limit. And yes, I just did make air quotes sitting by myself in my dining room. I do entertain myself when I make these videos, so I hope that's okay with you. Even if it's not, I'm going to keep going. So we're gonna factor in this one. The numerator is x squared minus 3x. There is a greatest common factor for those two terms of x. Take that from the first term, you're left with x. Take it from the second term, you're left with 3. All right, down in the denominator, this one's a little bit more complicated because of that leading 2. Okay, but it's going to factor into two binomials. The first term is 2x and x. That's how I get 2x squared. And then I'm looking at the end. The factors of 3 are only 3 and 1. I'm going to put the 3 here because I think I know where this is going. I think the x minus 3 is going to cancel. I'm going to check my work, though, to make sure it does. So I'm going to go minus here, plus here. If you need a factoring review, Google. Use the internet. Watch some factoring videos on YouTube. Now, the 2x plus 1 and the x minus 3, if I check that, I get a positive 1x in the middle, a negative 6x. 1 minus 6 is the negative 5 that I have over there. We cancel the x minus 3. And that's the thing that was screwing everything up. I couldn't plug in that 3 because there was a hidden x minus 3 factor that was making all the zeros. Now I'm going to rewrite what I have left. The limit as x approaches 3 of x over 2x plus 1. And if I substitute my 3 now, I'm substituting, so I'm not going to write limit anymore. I get 3 over 2 times 3 plus 1, 3 over 7, 3/7. And that's our answer for this one. The next strategy that we use for evaluating limits, when you see a square root, I want you to think conjugate. The conjugate is keeping the terms the same, but flipping the sign to a plus sign. And this will help us to simplify fractions that have radicals in them. So for this one, I'm going to rewrite my limit first. Limit as x approaches -1, radical x plus 2 all under, minus 1 divided by x plus 1. So the way that we use the conjugate here is we're going to multiply our fraction. I don't know why that was a highlighter, but that's okay. We're going to multiply our fraction by the square root of x plus 2 plus 1 over the square root of x plus 2 plus 1. So all I'm doing is I'm taking that numerator, flipping the minus sign to a plus sign. And not just the numerator, wherever the radical is. If the radical were in the denominator, I would do the same thing with the radical expression. All right? So what we do now is I'm going to rewrite this and simplify a little bit. The limit as x approaches -1 of what happens here. In the denominator, I'm going to keep my x plus 1 and my radical x plus 2 plus 1. I'm going to keep them separate, again, because I've done this before. I know where this ends up going, so you keep them separate too. And then the two conjugates, those multiply. So we're going to take radical x plus 2, multiply that together. The square roots cancel out. All right. Then I'm going to take radical x plus 2 times the positive 1. So I'm distributing here. I'm using the distributive property. The radical x plus 2 distributes to both terms, and it distributes to the positive 1. I'm not going to write that down because the next step is the -1 distributes to the radical x plus 2. And hey, those cancel out. Right? If you want to see this written out, if you're not like quite clear what's going on, let me know. I can add in something separate from the video just to make this super clear. But the middle terms cancel out, and that's why we use the conjugate. All right? And then the last two terms, -1 times +1, is a -1. So what ends up now happening in the numerator is I have x plus 2 minus 1 is x plus 1. I have a factor of x plus 1 in the numerator, and hey, look at that. I've got a factor of x plus 1 in the denominator. And these problems are set up so that this will happen each time, that I can now cancel out that common factor. And what we're left with is the limit as x approaches -1 of 1 over, because there's nothing, I canceled out everything in the numerator, so we have a 1 holding the place, radical x plus 2 plus 1. And if you evaluate this limit now, let's see, this is equal to 1 over the square root of -1 plus 2 is +1 plus 1, and that should simplify to 1/2 in the end. All right, so if I see a fraction, square root in there, I'm thinking, oh, the conjugate, I need to flip that plus sign to a minus sign or the minus sign to a plus sign in the radical term. All right, in the next few examples, we're going to be looking at some one-sided limits using our limit laws. And it says, evaluate each of the following limits if possible. So let's take a look. And actually, I'll tell you ahead of time, only one of these is possible. If you want to pause the video and think about which one, you should definitely go for that. All right, so let's see. Now, if I have the limit as x approaches 3 from the left and the limit as x approaches 3 from the right of this radical function. Now, if you think about substitution, right, both of them, if I just plug in 3, I get 3 minus 3 is 0 under the radical. Square root of 0 is 0. Cool. All right. But if you go back to the previous video, or think about what we did in the previous video, right, if I'm substituting, if I'm approaching 3 from the left, then that's like numbers like 2.9, 2.99, 2.9999, et cetera, et cetera, et cetera. And if you subtract 3 from any of the numbers that I just said, the answer will always be negative. 2.9 minus 3 is negative. Can you take the square root of a negative number? The answer is no, right? I mean, you can, but it's imaginary, and we're not there yet with calculus. Okay, 3 from the right, hey, I can do that. 3.01 minus 3, you get a positive tiny number, which, yeah, that has a square root. So for this problem, the limit, let me write this down, the limit, A, as x approaches 3 from the left of radical x minus 3, that one does not exist. And then another reason, another way to think about this is the graph of this function does this. 1, 2, 3. This graph does that. It's only defined on the interval from 3 to infinity. Right? That's the only interval on which the function is defined. Numbers less than 3, the function doesn't exist because it's the square root. We're not taking the square root of a negative number on a graph. All right? So that's why with this two-sided limit, when we approach from the right now, limit as x approaches 3 from the right of the square root of x minus 3, I can just say, all right, it's the square root of 3 minus 3. I can do this substitution. Square root of 0 is 0. It's defined over here. It's defined to the right of 3, but the graph doesn't exist over there to the left of 3. Okay, so that's why one side works, the other one doesn't. Now let's scroll down and look at another one that's a two-sided limit. Evaluate each of the following limits using our limit laws. A, we have the limit as x approaches 2. This is from the left of our function. Okay, but we've got to use the right branch. X approaches 2 from the left. That's the top piece of our piecewise function. So we have the limit as x approaches 2 from the left of 4x minus 3. Pretty sure I can just plug and chug into that. 4 times 2 minus 3 is 5. For part B, limit as x approaches 2 now from the right of our function is the limit as x approaches 2 from the right again of, now since we're approaching from the right, we have the bottom piece of our piecewise function, x minus 3 squared. I can just substitute 2 into that. 2 minus 3 is negative 1. Squared is 1. All right, now here's the big drawing it all together. Part C, what is the limit as x approaches 2 of f of x? Because I got a 5 in part A, a 1 in part B. Last time I checked, 5 and 1 are not the same number, so that limit does not exist. All right, there we go. This next problem has kind of a different approach, and it's, what do I do if I have a fraction and things don't cancel out? All right, so here we have a limit of the form, notice the form, k is just some number divided by 0. So if I evaluate my limit here, the limit as x approaches 2. So if I plug in 2 minus 3 in the numerator is negative 1. In the denominator, 2 squared is 4 minus 2 times 2 is 4. We get negative 1 over 0. I didn't write any of that down, but that's, you get this form, number divided by 0. Okay, so what's our next step? When we have a fraction, right, we're going to look to factor. So we'll do that. So let's do this. This is the limit as x approaches 2 from the left of x minus 3, x squared minus 2x. All right, good deal. Limit as x approaches 2 from the left, x minus 3 up top, x times, so we have the greatest common factor in the denominator, x minus 2. And you say, all right, you look at it and you say, what cancels? And the answer is nothing. All right, so when I have a fraction and I'm trying to figure out what cancels and the answer is nothing, I need a new approach. The new approach is we're going to break it up into two separate fractions, two separate limits that we look at. All right, and the two fractions, how you decide how to split this up into two fractions, I'll show you. Limit as x approaches 2 from the left. I'm going to draw my fractions first, and I'll tell you how I've decided to break this up. All right, which term is messing things up? Which term is causing the 0 in the denominator? It's this guy. All right, that's messing everything up. All right, so what we'll do is we'll take that x minus 2 and make him go playing by himself. X minus 2, you're your own thing. Stay over there. And then we can focus on you later. x minus 3 over x. Because that, I can plug the 2 into that. I can substitute 2 into that function. All right, so this is still, the whole thing is the limit. So we'll split this up now into the limit as x approaches 2 from the left of x minus 3 over x. I can do that. I'm going to be okay with that one. Times the limit as x approaches 2 from the left of 1 divided by x minus 2. That's an arrow. There we go. All right, so the first one, what do we get? If I substitute 2, 2 minus 3 over 2 is negative 1/2. Equal sign, times, times. All right, so I've got the first part of my limit answered. Now for the second part that's a little bit more involved. Let me change to a different color here. I'm going to do some scratch work off to the side. All right, I'm not sure, what's the answer yet. So let's look at some x and f of x. Let's use this strategy in this more challenging problem. What numbers are to the left of 2? Let's try 1.9, 1.99, and 1.999. So the first one, 1 over 1.9 minus 2 is negative 0.1. The second one, 1 over 1.99 minus 2 is negative 1.01. The third one, 1.999 minus 2, is 1 over negative 1.001. Okay, so that's what we get for each of our values. And now what I want you to do, I'm not going to do it. I want you to type those into your calculator. I'm not really going to know if you don't do it, but you should, and see what happens. Type them in, pause the video, type them into your calculator, see what happens for each of those values, and then unpause it, and I'll explain, or I'll tell you what that means. Okay, maybe you paused it and unpaused it, maybe you didn't. But what that means is that this limit is an infinite one, and it's approaching negative infinity because of what you got in your calculator. So what is negative 1/2 times negative infinity? A negative times a negative is a positive. The divided by 2 doesn't really matter. Infinity is massively huge. Dividing it by 2 doesn't make it any less massively huge. It's still huge. So negative times a negative, though, positive. The answer is positive infinity. So when you have these fractions, you factor them, nothing cancels out. We're going to split them up into 2 pieces. One piece will make we'll choose it to be the easy piece. One piece will choose to be the part that's making the 0. All right, that last one, a little bit more complicated, a little bit more involved. Hopefully I did a decent job of explaining it, but if you're still confused, please let me know. I'm more than happy to help you figure it out, but go work on the homework for this, and let me know if you have questions. Thank you very much for listening. Have a wonderful day.